So we'll start, sir. Hello, I'm audible.
Yeah, you're audible.
Nice.
My screen is visible, na? Yes, it's cross
Hi,
checking.
your screen is.
Slide. Suppose I show
Yes,
the
yes,
slide.
it is visible.
Visible, no? Okay.
Yes.
Fine. Thank you.
Good evening to all participants. Welcome back to the session 3 of day that is 2. First session of the day 2. So I welcome Professor Himanshu Bhushan Mishra from ISM Dhanbad. Before going to his talk, I like to briefly introduce about Professor Himanshu Mishra. Professor Himanshu Mishra, he received a BTech degree from BPUT in electronics communication in 2009 and MTech degree in communication and signal processing from EC department NIT Rourkela in 2012, and he obtained PhD degree in communication and signal processing from EE department IIT Kanpur in 2016. In 2017, he joined as assistant professor in electronics engineering department of IIT Dhanbad. Currently, he is working as an associate professor with the electronics engineering department IIT Dhanbad. His current research interests include the area of parameter estimation, detection and optimization for next generation of wireless communication technologies such as OTFS, IRS-OFDM, IRS-OTFS, terahertz communication, ISAC multi-antenna technologies. He is also focusing towards the real-time implementation of proposed algorithms on software-defined radio boards. He is currently leading projects funded by NRF, Department of Telecommunication, and DRDO in the domain of 5G 6G wireless communication. Till now, he has published more than 30 research papers in reputed journals and conferences such as IEEE Transactions and international conferences like ICC, Globecom, NCC, SPCOM, and many more. Furthermore, two of his research articles on OTFS waveform scheme have been listed as the best reading articles in the IEEE Communication Society. So I welcome Professor Himanshu Mishra, and I request him to take the charge and deliver his talk for today's first session.
Thank you, Professor. Thank you for this introduction. So, good evening to all. Let us start on this topic. So, here I would like to first explain mostly on OTFS, so why we are going towards OTFS for high mobility scenario. And I will particularly explain about some channel estimation techniques and equalization techniques in so whatever we have proposed. Okay, so that work will explain a brief manner, summarized form, and also I will give demonstration. Not means sorry. We have also a little bit work on hardware software co-design of our proposed algorithm. I will just brief on that. I'll show you at the end of the slides. And also I will tell about a little bit on RIS based OTFS systems. Okay, how we can make that system model and what are the research directions in this. Okay, so let us briefly we can start from some background of wireless channel. So if we know all this, all of us know that wireless channel, one critical parameter is that is known as small scale fading. Fading means that we are basically targeting the small scale fading. Why? Because that is creating lot of problems. Like it is coming. Why? It is due to the multipath and mobility. Multipath means whenever there are multiple paths getting added, so you will get what a total signal receive signal strength can be zero. That is very layman point of view. So what will happen that your bit error rate will be significantly degraded. Why it is happening? Because the channel can be on deep fade. So that is coming due to two scenarios. One is multipath, another one is mobility. So due to multipath, you have will face two key parameters. One is delay spread, and its inverse is coherence bandwidth. Similarly, due to mobility, two parameters we have. One is Doppler spread, and its inverse is your coherence time. So based on that, our channel has to be four different categories. So if you just look multipath, you have two categories. Either channel can be flat fading or frequency selective fading. You will go to mobility nature of the channel. So you have a two categories. One is high Doppler channel, or you can tell fast fading. One is slow fading. So taking one, you can take one from multipath, one from the mobility. So you'll get four different scenarios. Like channel can be either frequency selective fast, frequency selective slow, or fast and flat, and slow and flat, like that. So basically, for a simplicity perspective, we are basically using this one: frequency flat and fast fading. Frequency flat and slow fading channel. Whenever we are telling always that y is equal to some channel coefficient into data plus noise. This is a very simple mathematical model. Wn, I am considering this variable for the noise here. I am demonstrating. X is the transmitted signal, x of n, and g is, if we'll take that as for the channel. So y equal to g into x plus noise. So that is basically a very flat fading system. If mathematically you can write, but more practice, little bit you come more practice, like we are sitting inside a room, we are basically getting a frequency selective channel. So when a frequency selective channel, you can look here. So your channel will be this one, frequency selective, and it is not that much of fast. So we can take that for some frame duration, channel is almost constant. So in that duration, you can assume that channel, our receive signal will be means the channel will be frequency selective and slow fading channel. So that will result this mathematical model. But the received signal will be nothing but transmitted signal, and channel is act as a LTI system. Remember that in slow fading, there is, so time, it is not time variant, it is now time invariant. So channel is LTI system. So obviously transmitted signal will be linearly convolved with the channel and added with the noise. That's it. So this is a simple linear convolution. Okay, yn equal to the linear convolution of channel of transmitted signal plus the noise. If we'll go to the fast fading, like here, there will be no more, it will be not a linear convolution. Okay, it is a per channel one time instant, you can assume, you can take as a linear convolution, but this is not a linear convolution channel, because your channel is, you can take that channel as a LTV, linear time varying system. So this is the equation one will be demonstrating frequency selective and fast. We'll deal fast and two. Second model, second is we are sitting inside the room or moving little bit slower speed or pedestrian like movement we are doing, and that will be nothing but your frequency selective and slow fading channel. So you have to design the wireless systems for this kind of channel. Once you go for high speed, okay, like you are moving in bullet train or fast vehicle, whatever that, so it will, you will follow. So our channel condition will be frequency selective and fast fading. So that means in CISO system will follow this model. Now the question will come, what kind of systems we are going to, what kind of wireless systems we are going to propose for these scenarios. So if you consider for a simplistic frequency selective slow fading, what will observe here? Frequency selective slow fading will see that you receive signal at any mth time will be a transmitted signal at that time plus some intersymbol interference. We'll always observe intersymbol interference for frequency selective slow fading channel. So that intersymbol interference will be creating problem to decode your transmitted signal. Okay. So what will happen that you have to propose some technique, or you have to know develop some techniques so that it will nullify the intersymbol interference. If you so you can use some equalization techniques like zero forcing, MMSC, but still will not combat it to exactly ISI equal to 0. That's why one very powerful modulation technique came, that is known as OFDM. So that 5G, 6G, whatever you will go there, OFDM is the key waveform technique that no one going to leave it. So it is going to be useful everywhere. Why? The main reason, first point is it will reduce the intersymbol interference. It has even second advantages. What is the second advantages? You can see that this is a transmitter, this is the basic transmission structure of the OFDM and receiver structure of the OFDM. So I'm not going to detail into this thing. So here, one very important point that you can see that your transmitted signal, what will happen to the transmitted signal? Once it will be transmitted here, what will happen? Forget about anything. In transmitted signal will be get linearly converted to the channel and you will receive signal, right? So that means something we have to do to remove the effect of channel at the receiver, right? So that you can remove the ISI effect. So this thing, we have to do something that if you can make it zero, it means what? That means frequency selective channel, if you can, some technique, if you can make it frequency flat channel, so then we can easily equalize the system because there will be no ISI in the frequency flat. So if you can do something, what will happen that since there is a linear convolution operation will do, we know that from signal processing concept, a linear convolution can be written as a circular convolution form. It can be equal to a circular convolution form. For that, what you have to do, some processing we have to do. We have to increase the block length by adding some thing that is known as cyclic prefix. Okay, if you add cyclic prefix will be taken from the right part and it will be just appended. So what will happen when you that means the transmitted signal, time domain signal will contain cyclic prefix. It will be linearly converted, but after removal of the cyclic prefix, you will get a circular convolution signal. Transmitted signal, channel, circular convolution, and that is the received signal. Then if you have the Fourier analysis, we all of you know that FFT of a circular convolution will be multiplication of these things, the individual frequency responses. So that concept can be incorporated in the OFDM to make this ISI to be zero. So that is happening here. You can see the transmitted signal here. I have written mathematically this thing as a linear algebra point of view. So that also you can write as a linear signal processing, that what you have studied from the DSP in normal book. So you can write in that form also. So what will happen, the transmitted side, you will do the IFFT. This is the IFFT. That means you can write F Hermitian, F if the FFT matrix. So IFFT once you do, then yeah. So after removing the cyclic prefix, what will happen? This is the things what will get. X is the transmitted signal, right? Transmitted signal in frequency domain that has to be done IFFT as the transmitter. So this is the transmitted signal. This is the transmitted signal, and you have to do IFFT. Then you will get the time domain signal. X is your time domain signal. Okay. So this is the frequency domain signal. So time domain signal will be transmitted. This X has to be appended with the cyclic prefix. It will be get converted with the channel. After removing the cyclic prefix, what will happen? This expression you will receive. Receive signal will be equal to circulant matrix. This channel is in form of circulant matrix into the transmitted signal. What is the time domain signal plus noise? Now the question is, this circulant matrix is a very interesting point. You will get this circulant matrix only if channel is slow fading. This is very keep in mind. You will not get this expression if channel is frequency selective and fast fading. That is a very important point. So this circulant matrix has an interesting, if you know the decomposition of a matrix. Okay, if you find the SVD, singular value decomposition of a circular matrix, what you can observe that it can be written like this. F Hermitian, this is the left, that is eigen matrix, you can tell this is the IFFT matrix, F Hermitian. Okay, this is the gamma. This one is, sigma. So this one is nothing but this is a diagonal matrix. This into F, F is the IFFT matrix. So this diagonal matrix, it contains what? All the diagonal elements are nothing but channel responses, frequency responses are different tones or different subcarriers. That will be this thing. So that's why you will get better advantages since you can express the received signal in the circulant matrix form. That's why you can able to express this thing. So then what you do the mathematical operation. What you do, the transmitter side if you do IFFT and receiver side if you do FFT. IFFT means what? You have to multiply F Hermitian. FFT means what? You have to multiply F. If you do that, you will obtain receive signal. After FFT operation or DFT operation, you will get Y equal to that sigma into S plus noise. What is S? S is your transmitted signal in frequency domain. That means whatever signal you taken from the constellation that you are getting, so that relationship with the receiver. That means this simple the relationship between received signal and the transmitted signal from the constellation. That you got relationship with a diagonal matrix. So what will happen? It means that received signal at kth subcarrier, equal to the channel impulse response at kth subcarrier multiplied the transmitted signal at kth subcarrier plus noise. So it's very simple mathematics. So what you got, you can just see this equation, compare with whatever equation you have, this equation. That means you have transmitted, instead of transmitting in time domain, what you do, you transmit the same signal in the frequency domain and apply all the IFFT at the transmitter and receiver FFT, all these operations, include CP, remove CP, you do all these things. Finally, you will obtain this expression, this one. This expression, what you will obtain, this is nothing but your received signal. So now, whatever signal you are transmitted, there is no ISI. Okay, this is simply channel into data. So that means a very simple flat fading type expression you will got. So that means you can easily use a one tap equalizer. That means simply you divide channel into received signal, you will get the data. That means that is another big advantages of the OFDM. That means using a parallel detector, you can detect all the subcarriers at a time. So just use one type equalizer. You no need to do any matrix multiplication, any inversion of the calculation also you no need to do. That is something big advantages of a OFDM. So now the next disadvantage that I told, that if you go for the highly frequency selective, highly time varying channel, what happened? So this signal, this matrix will be no more circulant. Due to this, what will happen? Some additional components will come. That is known as inter-carrier interference. Here, some additional components will come. So then you will face again problem of detection. So that's why. So recently, you can tell the 3-4 years back. So we have a very interesting modulation technique came, that is known as the orthogonal time frequency space. So name itself gives something like, you can confuse that what is the meaning, why it is orthogonal time frequency, what is this reason, the name. So let me explain all these things. So what is OTFS? This is a short form, you can tell that's OTFS. What will happen in OTFS, that in OFDM, what you are doing is you are transmitting the signal in a frequency domain, or you can tell the time frequency domain. You can make OFDM symbols like one symbols at that different time. Okay, so one symbol, OFDM symbol having many subcarriers, then next time another OFDM symbol. So like that, you can tell the time frequency frame completely. But instead of doing that, what you can do in OTFS, you do transmit the signal in delayed Doppler. So why we are doing this thing? So before explaining the transmitter model, I will just now go directly into this thing. What is this? This point is known as representation of wireless channel. Wireless channel, if we can represent, wireless channel is a black box, right? We can represent it by some impulse response, or you can tell impulse function of this. Either it can be represented 4 different variants. What is that? We can represent a time variant impulse response. Since channel is a time varying system, right? LTV system I told. So it can be represented as its impulse response. You can write G of t comma tau. T correspond to time, tau correspond to delay. It has a delay as a function and also time another function. Another kind of representation we can do in frequency domain, that is known as time frequency domain. It's just its Fourier transform. Then another also you can represent in delay Doppler domain. Another one is Doppler and frequency. Our main concern, OFDM, what we are doing, we are considering channel in time frequency, right? The channel frequency response. So that is only at different time, what is the channel responses. So we are considering slow fading channel, that's why we are ignoring this T factor. But in practice, different time we will have a different frequency responses. So now this thing, if you can analyze a pictorial form, that if you have a channel, wireless channel, if you see this frequency, time frequency response and delayed Doppler response, what you'll observe and how they are related. So time frequency response, you can get from time frequency to delayed Doppler, that is a 2D transformation. Since it's a 2-dimensional function, you will get 2D transformation, that is known as symplectic finite Fourier transform. If you do that in its reverse, you do ISFFT, inverse symplectic finite Fourier transform. Okay, so now let me tell you that how this channel will represent. Just here. So this is a scenario, right? This is something like, this one is blue one, green one, sorry. It is being receiver, okay, receiving antenna. There is a transmitting antenna. This one is the transmitter. So there are many paths, okay, many paths, through many dominant paths. You can tell the critical, there are 3 paths are there, through which it is getting dominated and received here. 3 or 4 paths, sorry. So 4 paths are there. So each path has each path will have, if you study the wireless channel, the complete, you can see any fundamental books like David Say or Andrea Goldsmith. So what you see that channel response, what you can see that each path is associated with a delay and also associated with a Doppler. So that exact expression you can get if you express the channel as a delayed Doppler form. So okay, so if we, so that thing we can hear here you can get it at different delay. So you can see the yellow one at a very less delay you will get one Doppler. So you can see at each, for each path you have a delay and Doppler. These heights are nothing but the gain of the path, right? Whatever paths you have, that is a channel coefficient. Its gain is denoted by this height of these pillars. So what you observe? Four dominant paths, four number of only four number of paths you can see here. But here what you observe? There are many. If you see same wireless channel in time frequency domain, what you see that at different time and different frequencies, there are many paths you will see, because that each path will have a different times, it will vary everything. We are seeing wireless channel, you are looking instead of delayed Doppler, you are looking into the time frequency. So what you'll observe that here many pillars, here only four pillars. So that is critical difference, that one can easily say that by looking this one, this is sparse nature, why it is not in sparse. So if you want to estimate the channel in delayed Doppler form, what you can see, the only four tabs you need to estimate. You don't need to estimate many tabs. Okay, that is one kind of, for example, this more clear set you can sit here. You can see here. That means here you have a transmitter, you have a receiver here. So three paths, each path like this is moving in this direction. So obviously what you get, this is a direction. So it has a very less delay. So this you can see here, delay is zero. Delay is zero, you have a some Doppler. Doppler will come when there is a formula, Doppler shift formula, all of us know that. So that formula depends on the velocity and the carrier frequency. So based on that, you have some Doppler will be there. So then once you another, see here it is getting reflected by this one. So what will happen? If reflected by this one, it is moving high speed, so you'll get more Doppler. And another point is, you since it is getting delayed little bit more distance, this reflector is there, so you will more delay. So similarly, you will get purple one coming in opposite direction, so you'll get a negative Doppler. And so obviously it is more delay is there, and you will get a more delay. Obviously the distance, the reflector presents a little bit larger distance than the other reflectors, so you'll get more delay. Another thing, the width of the circle based on the gains, channel gains. So more further the distance, all of us know that the power will be decreased, so you will get what, you'll get the reduction in the channel gain. Okay, so based on this is the example. Another one interesting thing I will tell about the delay Doppler point, that is known as, in addition to, all of us know that coherence time. What is the coherence time? Coherence time, the time duration over which channel is constant, and after that channel is fading. Means if it is coherence time is higher, so it is a slow fading. If coherence time is smaller, it is a fast fading. Now there is another topic, another interesting thing, that is known as geometric coherence time. Geometric coherence time means what? It depends on environments. So it will affect critically on the delayed Doppler channel. This delayed Doppler, whatever channel you have, after taking some millisecond, exact time I have not forgotten, after taking some, but that is greater than the coherence time. If you take the greater than the coherence time, same scenario, you have measured that, what you observe here, these two are exactly same. There is a little bit change on this one. That means you can tell it is approximately constant. Channel is approximately constant. It is approximately constant in delayed Doppler domain, even if we're going, even if we measure the channel after coherence time. So that is a very interesting advantage of a delayed Doppler channel. That means delayed Doppler channel is almost constant within the coherence time, you can tell. Because it is, even if larger than the coherence time, also delayed Doppler channel is almost constant. So that's why instead of working on the time frequency domain channel, if you can work on the delayed Doppler channel, we'll get better advantages. We can make the system to be more reliable. Now the question will come, how can we do in the delayed Doppler domain? Then that gives you the, then you have to do everything, modification has to be done the transmitter receiver. Then only you can estimate the delay per channel, you can do these things. So then the concept that things will come, that is known as OTFS. What is this meaning is, you transmit the signals in delayed Doppler domain. This is the two-dimensional signals. You transmit it, then convert this signal for the transmission. What you have to do? We cannot transmit a two-dimensional signal, right? We have to convert into the one-dimensional signal. So this will be converting to the one-dimensional. So that conversion method varies. You have two different steps. Two different methods are there. So one I'm explaining here. What is this? There's two different steps you are following. First step, what you are doing? You are converting delay Doppler to time frequency. That you are doing through ISFFT. Then you are converting the time frequency to time by Heisenberg, or you can tell by IFFT. IFFT will convert from frequency to time. If you use the one column wise one IFFT, so you will get a time, completely time frequency will be converted to time. This is the Heisenberg, or you can tell as IFFT simply. So at receiver, you have to do the reverse operation. This is time domain, converting time frequency by Wigner, which is the reverse operation of Heisenberg. Then time frequency to delay Doppler done by the SFFT, simply active finite Fourier transform. Now, why people are doing this thing? Another, there is a method that I am not mentioning here, that is known as, you can tell simply, Jack transformation. So inverse Jack transformation, that will do transform directly from delay Doppler to time. Okay, this will be not doing that. Here you are taking two steps. Why you are taking two steps? Because we have a means OFDM chip is available right now, IC is available. So OFDM, everything, all the algorithms we know. So if you just this complete part, you can take as the OFDM. Why? Because transmitter side you have IFFT, receiver side you have FFT. This Wigner is nothing but you are doing FFT operations. So that's this you can tell the OFDM. To make compatible with the OFDM, whatever OFDM chip, or you can tell OFDM things are available with us, how OTFS can be designed using OFDM. So that's the question came into the mind, and due to that only, so people thought that let us go in that manner. So first to convert the delay Doppler to time frequency, then everything will be taken care of by the OFDM transmitter. So that's why here you can think that if we use a transmitter side processor or precoder as a ISFFT and receiver side as a SFFT, so by these two blocks club with OFDM, you can get OTFS. But there is also a lot of negative points if you're doing that. So okay. So let us not discuss on that. So let us come to this system models. So if you do this thing, as I already told, this is the transmitter side. So you have the blocks like a delay Doppler. These are the delay Doppler things, and this will convert into time frequency. You can see this one, the time frequency delay Doppler. Okay. So if you take the complete time and delay Doppler, accordingly you will get the resolution. See, NT is the complete time. So what you will get here? Doppler resolution 1 by NT, right? So M delta F, the complete frequency of a or you can tell bandwidth of the one signal frame duration, NT, and frequency bandwidth is M delta F. Okay, so M delta F means here it is M delta F means it will affect in the delay resolution. That way, what is that? M 1 divided by M delta F. So accordingly, you can make the time frequency grid along with the delay Doppler grid. So basically, you can tell N, here I have considered N as the number of Doppler bins, M as the number of delay bins. That's it. So accordingly, we have to design based on our requirement, what kind of Doppler we are going to handle. Accordingly, we have to design everything. Okay. I'm not going to that how you will design this thing. So let us come to the transmitter side. What we are doing the transmitter side, Fourier transform, ISFFT we have to do, inverse simplective finite Fourier transform. So this is how delay Doppler converted into time frequency. Heisenberg, time frequency converted into time. Okay, this is the simple mathematical equations, equation 9 and 10. Then receiver side, what you have to do, your transmitted signal. Okay, so this equation explains what? If the transmitting, what you have transmitted, time domain signal S of t, you should have some equation with the RT, some relationship RT with S of t. What kind of relationship you can make? That depends. The mathematical relationship critically depends on what impulse response format you are going to consider. That means I can tell you this expression here. Yeah. 6, 7, 8. These three things. First thing, what you are doing here, you are considering here the channel as a time delay. If you consider time channel impulse response in time delay, in transmitted signal is S of t. This is your receiver equation. Receiver signal will be this integration of this thing. That means simply it is like convolution form. But here, if you go to delay Doppler, it will not look like this. It is double integration in these things. Equation 7, 6 and 7 is varying. That means whenever you are considering a channel response, that means if you're considering time delay or you're considering delayed Doppler, accordingly your receive signal expression will vary. Similarly, if you consider time frequency, your expression will vary. In this case, our interest is only 7 equation. Because why? Because we are considering channel impulse response in delayed Doppler domain. So here that's why your receive signal will be looking like this, equation 11. Then you have to do lot of processings and all that, Wigner transform and all these things. So after doing Wigner transform, okay, what will happen? You have to use, obviously, transmitter side there is a pulse shaping you have to do, receiver side you have to pulse, then there is a cross ambiguity will come. So cross ambiguity means what? That means you have to see that when you convolve, very simply layman point of view, so what you will see that this is a two-dimensional pulse, right? So this you can see that this you can be spreading, it can spread over the adjacent symbols, or it can be localized. Okay, so it cannot be localized actually practically, but it will definitely spread. But we assume here two scenarios. One case we'll assume that it is perfectly localized. One case we'll assume that it is getting spread. So that's why I'll tell you here two mathematical models. One is ideal, one is practical case. So let us forget about ideal practical, but this expression will hold for all cases. What is this expression? This expression denotes the relationship between transmitted signal at time frequency and received signal at time frequency. That means you can find the relationship between here and here, this and this, YNM and XNM. But this is a very important point. And finally, we'll have to relate what is the relationship between YKL and XKL. Then you are after that you can design any channel estimation, equalization, all these things. So before that you have to develop the system model. Okay, so that there I have written the expression of YNM and XNM. What we have written there? Expression of YNM and XNM. Okay, here you can see this is some kind of double type. You can okay, this is a channel at different delay and time. Sorry, time and frequency. N correspond to time and M correspond to frequency. And transmitted signal at different time and frequency. You have this relationship. That means what you observe that that means it is simply you are getting interferences. Like one time frequency will have interference with others. This expression, see, this is important point here. Here this expression you are getting like this, but if you consider a slow fading channel, frequency selective slow fading, this expression will be changed. You will get like wavetable. You will get only Hn with X plus noise. You will not get any interferences. That's why here the point is you will get only time and frequency with some interference you are getting. Why? Because you have considered the delay, you are considering a highly time varying channel. That's why you are getting this expression. You will go to slow fading channel, automatically this will convert into that you have only one tap multiplied with the transmitted signal at that frequency plus the noise. So that's why this expression will be denotes that you are working with the OTF as highly time varying channel. If you go highly time varying channels, you will get this expression. Now let us see what will happening if you go for the ideal pulse shaping. So if you go for the ideal pulse shaping, here I will let you know. Yeah, this is something SFFT. After Wigner, you will do SFFT. That means you are converting the time frequency to the delayed Doppler. Okay, let us come to the ideal pulse shaping. So this is something known as your channel representation or delay Doppler. Obviously, each channel, each path has a delay and Doppler. That's why you can represent this as like this. Very simply, this is the gain, channel gain at ith path, and it has a delay tau I. Nu I is the Doppler. So you can represent this as the impulse response, channel impulse response, the delay Doppler domain. So let me come to the point. This expression, okay, this expression is a generalized expression. Relationship between time varying channel, the relationship between receive signal at time frequency domain and transmit signal at time frequency domain. So let us come to the point here. Yeah, using ideal pulse. What will happen if you leave ideal pulse? The cross ambiguity function will come in that equation actually. That you are assuming that it is perfectly localized. What is the meaning that? It means that pulse is not getting interfered with other. That means that it is not spreading. It is, that means one symbol will not get interfered by the other symbol. If you do that, if you assume this expression, what will happen? Whatever the expression I told there, it will means the modified one, it will be, that means it will result this expression. See this expression. What is this expression? The transmit signal at time instant n and m at n time instant and frequency, mth frequency multiplied with the channel at nth time and mth frequency. That's it. There is no interferences. Here you can see that here you have the interferences, but there is no interferences are there. This is OTFS. You have considered here what? You have considered a time varying channel, but still you are getting a similar expression like WaveDM. Here, this expression. This is similar kind of expression like WaveDM. But you have done here what? You have done a time varying channel, but that's it is orthogonal time frequency. That's the name is given at orthogonal time frequency. But that you got by assuming that you are dealing with ideal pulse shaping. Okay, that kind of assumption will not give you in case of WaveDM. If you use WaveDM for highly time varying channel, so you'll not get this kind of expression. But in OTFS, by assuming your cross ambiguity function like this, you can get the receive signal like this. So that's its name. You can justify as orthogonal time frequency. Okay. So there is no intersymbol interference in the time frequency domain. And this will, after the Wigner, what you have to do? You have to do SFFT. Then what will happen? You will get the relationship between received signal at delayed Doppler and transmitted signal at delayed Doppler. This is somewhat you can see that this is a two-dimensional circular convolution relationship. That is also another interesting relationship. That is the relationship between what? And this is the relationship between the received signal, this XKL and YKL. So what I have done is I have written the relationship between YNM and XNM and also YKL and XKL. For one scenario, ideal pulse shaping. Ideal pulse shaping, these two relationship is very, very important that you are doing ideal pulse shaping, this expression and this expression. You can take any one to do your system design. If you take this one, what is the negative point? Every time and frequency you have to take the channel. Here, what is the positive point? You have a few number of paths, right? Few number of paths means few number of channel taps you have. So it will be getting only few number of channel taps. So you will getting your complexity, receiver complexity will be very small. So that's why we are considering generally this expression, this mathematical expression. But you can do with this expression also. This is the relationship between received signal with the transmitted signal in time frequency domain. This is in the delayed Doppler domain. If you do that, the main advantage will get what I told again and again. We have a less number of paths. We are dealing with a less number of paths. So definitely the complexity part will be reduced at the receiver. Okay, this is for the ideal case. So in more, if you enter into a little bit practical scenario, practical means you will not assume that this thing is like this. You will assume that there is something, the pulse is spreaded. Okay, there is some side lobes in the pulse. So what will happen? That will give right. If you write the same expression, time frequency domain, so you will get, as I told, this expression already you have written previously. There I have not expanded. Here you can see the expanded form. You have inter-carrier interference and you can tell inter-symbol interference. Carrier means it in the frequency domain, it is time domain. Time domain you are going inter-symbol. Yeah. Frequency domain you are when you are getting interference, that is known as inter-carrier. Both inter-carrier and ICI and ISI both will come into the picture. You will consider the pulse shaping, practical pulse shaping. That is the practical thing. And here, what will happen? This relationship will give you, if you consider this, you will be very difficult, face lot of difficulties to get back the actual transmitted signal. This is the time frequency form of the transmitted signal. So what we will do, let us convert into the delayed Doppler. So see an interesting expression 14. Okay, in delayed Doppler domain after taking the time frequency, practical pulse shaping scenario. Now you can make a difference between this equation 14 with this expression 12. What you got? Here you have HI prime, right? The HI prime is the channel gain for ith path. But here what you got? Here in addition to HI, you have something BIK, this is a phase factor actually. That is a phase factor, which is nothing but a phase that depends on some parameter values. Li, Ki, nothing but the indexes correspond to delay and Doppler. Okay, Li is correspond to delay and Ki is correspond to Doppler. So basically what you got the difference? Here you have a phase coefficient multiplied with HI, here only HI. Okay, so that is something that if you know this, you can easily decode the transmit signal. But this one is very difficult to do. Why? Because that's ICI is coming, ISI is coming. That's why we are that's why our equation 14 is very useful. The relationship between the delayed Doppler, transmitted and receiver, the relationship will be very useful to do all the receiver processing, right? Channel estimation, equalization, and all. So this thing will give you the vectorized form. This is y is equal to hx. Let us write that symbol by symbol expression into vector form. For ideal perceiving, what do you get this relationship? That delay Doppler. So that is one case. In ideal case, what you got? Why ideal case we got that this is just two-dimensional circular convolution. So that will gives rise to a circulant matrix. This is known as a block circulant matrix. H is a block circulant matrix. H into X. Okay, so this is the interesting thing. You can use this expression to develop any novel algorithms. But this is for the practical ideal perceiving. If you go for the practical case, this is how sparse block circulant will come. I have taken one example. Okay, some example you can see more detail in the slide. So you can see here that I'll not go to detail. Once the slide will be shared, you can easily understand this thing. Okay, this is the very simple thing. Block circulant means what you can make a different. Here you have two different paths. Each path has some delay in Doppler. First path has zero delay, zero Doppler. Second path has one delay, one Doppler. So accordingly, you will make all these things. Okay, you will make a sparse block circulant structure. Okay, that block circular structure you can get only if you're using assuming the ideal perceiving. Now if we'll go with the practical perceiving, this is somewhat okay, practical perceiving scenarios. What will happen? Yeah, here you can look in this expression. I'll only my concentration is only in the channel, how the channel is looking. Their channel is a block circulant, here channel is not a block circulant matrix. Okay, it is something look like the channel gain pi. This is some kind of permutation matrix. Li is the delay. Delta is a diagonal matrix. Ki is the Doppler index. So this will give you H like this. Okay, so your R is equal to the received signal H. The received signal will be in time domain is written, and H is in the this expression. S is the time domain plus noise. That means the thing is this H is no more circulant, so you have a different structure of channel. So accordingly, you have to propose different algorithms to get back the transmitted signal. So this is the relationship in time to time domain. That means the transmitted signal in time domain, received signal in time domain. Same relationship you can also get in transmitted signal. This expression or the expression, yeah, this is y the received signal in the delayed Doppler, x is the transmitted signal in the delayed Doppler, h effective is the effective matrix, effective channel matrix, or you can tell effective delayed Doppler channel matrix that you do all the processings like Wigner transform and SFFT. Then you will get this expression. Okay, this expression H effective. This one. This is H is what? H is what you have considered here. This H you substitute here. You will have all this due to Wigner and SFFT. You will get this channel matrix. So now your received signal or delayed Doppler will be equal to channel matrix into X. This channel matrix is no more circulant. That means we are now, you can compare this expression with what you have done previously for the ideal perceiving, this expression. Yeah, this one. Both are delayed Doppler domain, but here H is block circulant, there H effective we have written. That is not the block circulant. So here. So now here there is a this is particularly you can tell as the cyclic prefix OTFS. These are different than wavedim. What will happen wavedim? Each symbol you are transmitting what? Yeah, you can understand here. Each symbol you are transmitting wavedim symbol one, you have to add one cyclic prefix, remove one cyclic prefix, right? But here what you have to do, complete frame you have, delayed frame. There you add the CP and remove CP. So that's why you are not going to lose any. You are going to get better spectral efficiency than if you'll go use like wavedim. Okay, that's why I told you if you directly use wavedim and put a precoder and a postcoder like ISFFT and SFFT, you will be losing lot of information. That means what you are doing is you are wasting your time frequency resources. But here, what you are doing by single CP length is how much L. There, if you use that by traditional wavedim method, each wavedim symbol has one CP. So many cyclic prefix you are going to use. So that's why that's why this is a better option, CP OTFS, that you can remove by CP OFD. Okay, CP OTFS will be better option for OTFS. But here, what you have to do is your transmitter side have to do ISFFT, Heisenberg, receiver side SFFT, Wigner. That means instead of telling this OTFS, we can tell us cyclic prefix OTFS. Because why it is required? To one frame will not get interfered by the other frame. That's why you have to put the cyclic peaks. The length of cyclic peaks, obviously, if the length of channel is L, so it will be maximum length, it will be L, minimum length will be L minus 1. 4-tap channel, the CP length will be 3. Okay, so now this is the mathematical system models we have. Now let us come to the what we have to develop here. How to decode. First question will come, how to decode this transmitted signal. When we are decoding means what? We have to look this system model first. You have a system model, this thing. Okay, so you have H, you have to get X, Y. So there is some method earlier, many they have proposed, like one straightforward method, all of you know that, map detector. That is the optimal detector communication. So map detector, if you do that, this will be highly complexity because X size will be higher. If you take practically subcarriers, how many subcarriers 5G is using? I think 3000 means more than 3000. That will be, or you can tell the that means more than 3000 subcarriers are being we are using, right? If that many subcarriers along with n is a Doppler bins, so you can tell that how many complexity if you will go symbol by symbol detection in map detector, you will complexity will be significantly improved, significantly higher your complexity. So what you will do? If enhancing complexity means it will degrading your receiver, means the circuit complexity, everything will be, it will consume more power, more time, everything. So then, so that's why people are proposed a message passing detector which will give you a near to map detector but having less complexity. That will be done in this paper. So interested people, you can follow this paper. But what additionally we can do, we can also follow a linear, that is a non-linear method, still it is non-linear. So hardware implementing a non-linear, so it will be iterative manner. So instead of doing that, we can go for a linear detector. So there are critically two different kind of linear detector we have. One is zero forcing, one is MMSC. So if you apply that zero forcing, what will happen? This is a system model. Zero forcing, if you apply here, see, this is the zero forcing equalizer, H Hermitian, H inverse, H Hermitian. So now the question will come that how you will compute this inverse. Inverse computation itself will be high complexity. So that's why many researchers propose a low complexity manner computing this ZF and MMSC. Okay, that is also one research direction. So you can see some papers where you can see that how the low complexity linear equalizers has been proposed for OTFS scenario, and it exploits the channel structure. First, you can see this paper by Professor Chokalingam's group. What they have done is they have exploited the channel block circulant structure. I told you they have developed for the ideal scenario. They exploit the channel block circulant structure, and you know that SBD of a circulant matrix is what I told, that thing, just IFFT and diagonal matrix and FFT. That will explain that we explore, so you will reduce the complexity very small. So similarly also many people have done for the practical pulsing. We have also done for the MIME OTFS, so you can follow our papers for this. Another thing, let us come to the channel estimation. Channel estimation, how to do? Channel estimation can be done, see, since channel can be represented all these four forms, in OTFS case we can do channel estimation either in two domain. We can do either delayed upper domain or we can do either time frequency domain. As I told you that if you do time frequency domain, we have to estimate many channels. If you do delayed upper domain, we can estimate only few number of channels. That means why? Because channel is sparse in nature in delayed upper domain. That's why we have proposed methods how to estimate the channel in delayed upper domain. So one work we have done, like few work they have done is conventional pilot based channel estimation. Then they have proposed embedded pilot based channel estimation. Okay, I'm just showing you some brief. Okay, this is how people have done the research. This is OTFS frame. They have the data, this is the pilot frame. What they have done is one pilot, this is known as embedded pilot based channel estimation, that was done by some research group of Professor Bitterbo. So what they have proposed, one pilot they have taken in the center, many zeros they have, and they have few data. Okay, this is one OTFS frame structure. These zeros why they put, or you can tell the guard symbols, they are putting the guard symbols because they do otherwise it will get interfered. Pilot and data will get interfered, so that you cannot estimate the channel, because the estimation of the channel requires the receive signal. Okay, receive signal should be contain channel and pilot signal. This should be function of channel and pilot signal plus noise. It should not be function of the data. If it function of the data, then will get interfered. So to make that, so then you have to be put the zeros. Okay, so then how they have developed, how many zeros, everything will be depends on number of maximum Doppler, what is the maximum Doppler shift, what is the maximum delay. Accordingly it will vary. More number of maximum delay, so more number of zeros. That's the negative point here. If you're putting more number of zeros, what will happen? You're unnecessarily reducing the spectral efficiency. So that's why we have proposed. So this is how the channels, how the locations you will decide where to be pilot, where to be data, and all these things. So this I have written here. Okay, next is embedded pilot. Yeah, channel estimation will be very simple. After getting the pilot one, you can simply receive signal, divide with the pilot, you will get the channel. Then accordingly you can estimate the location. See, one interesting point here in OTFS case, when you are doing the delayed Doppler channel estimation, you no need to only estimate the channel gain. You have to estimate also location. Okay, at what delay and what Doppler you have the channel. So you have to look complete pillar, you have to estimate, but grid, but time frequency everywhere you are getting estimated. Okay, so everywhere you are doing, so you don't need to any particular things. You are doing complete block, but here you are not doing the complete block. Since it is sparse, you have to do only few blocks, few grids you have to estimate. So that's why in addition to doing channel, you are estimating three parameters. What is one? First one is the channel gain, another one is what, delay shift, another one is Doppler shift. So three parameters you are required. So this everything, all three you can find from this embedded pilot based method. Another we have proposed, another one is superimposed pilot. This is our work. So we have proposed here, what we have done is we are reducing the spectral efficiency in comparison to embedded pilot. So you can detail things, you can follow this paper. So let me not explain all these things here. I will explain something interesting after this. What is that? Yeah, let me superimposed training. If you pilot based channel estimation, if you want, you can follow that paper. So in something I'm going to explain here, we have a limitation of time. Okay, what is that sparse channel estimation? Since OTFS delayed Doppler, OTFS is sparse in the delayed Doppler domain. What you can see here, we can OTFS channel estimation, we can formulate as a sparse recovery processing. So what can we do? This is the receive signal. Okay, receive signal, you can write, it is a pilot matrix. This is channel vector. But the channel vector contains all possible delayed Doppler locations. There is actually m into n possible delayed Doppler locations, out of which only few p number of parameters are non-zero. That means the h vector is a sparse. So here we not only estimate the channel gains, we have to estimate the which locations of the unknown where there is non-zeros are there. That means what we are getting, where non-zero locations of h is nothing but the delay Doppler locations, and the gain is nothing but a channel gain. Okay, if we estimate everything, so here that means we are getting the all complete information like channel gain and delay Doppler locations. That's why. So this can be easily formulated as a sparse recovery problem. So sparse recovery problem, there is, to solve the sparse recovery problem, we have various SBL technique, greedy sparse technique, two different techniques we have. One is SBL, sparse Bayesian learning. It has a negative point. What is the negative point? Channel statistics you have to be priorly, you should know, which is a practically very difficult. If you know the priorly channel statistics, practically we don't know the channel statistics priorly, right? Many assumptions, mathematical assumptions you have to do in sparse signal processing, sparse Bayesian learning, sorry, Bayesian, because that is Bayesian form means you have a lot of modeling you have to do, which is a prior assumption. That is wrong, then you are not going to be then your practical system will be fair, definitely. So to combat that, another technique is that is known as greedy sparse recovery, where you not record any statistical knowledge about the channel, anything. Then you have few techniques are available. What is there in our case? In our case, more practical things is what we don't know anything about the channel. We don't know how many non-zero paths are there. That means we don't know the number of delay Doppler paths also. If you know that, you have some different technique you can apply, sparse recovery technique. Okay, if we don't know the how many, suppose there are 4 number of channel taps, but we don't know the practically receiver how many channel taps you have. We don't know that is. So what you can do is, so these are existing techniques. They are what they're assuming priorly they know the number of delay Doppler channels. That means priorly they know the sparsity. But what we have proposed in our work, that is known as this work we have proposed. sorry, this one, two choice hard thresholding pursuit algorithm. This one is what we are not assuming that we know the previously we know the sparsity. Without knowledge of the sparsity, so this is somewhat your problem statement. Okay, so this okay, so here, so our papers also we have the paper, this one is. So problem statement, what is to develop a low complexity sparse signal recovery technique to estimate delayed of the locations and the associated CSI without the explicit knowledge of the delayed path. This is one interesting thing that gives the first paper. This one is the IEEE wireless letter. This you can go through. They'll get the knowledge how we are developing the two choice hard thresholding pursuit algorithm technique to estimate both delayed of the locations along with the channel. So what we have done here, basically this follow some methods. First you have to do what? Input initialization, iteration. What will happen? It will estimate the support means what? Locations. Then it will estimate the channel. Okay, these things will happen here. Basically it will happen these two: support estimation, channel estimation. So these two choice, but it will happen in two choice. I will tell you here. Yeah, here you can understand easily. So we are, instead of two choice means what? We have taken one is upper bound of the sparsity. Instead of assuming that we know the exact sparsity. Suppose exact sparsity is 4, but there is upper bound. What is upper bound? It cannot go beyond m into n. It's always. And another point, it cannot go beyond a L max into K max. What is L max? L max into K. L max is the maximum delay. K max is the maximum Doppler. Maximum delay and maximum Doppler of a wireless channel, that we know. That always we know that any wireless system has some maximum Doppler and maximum delay. It cannot go beyond that. That upper bound we can take. That is a very large assumption that we know. So what it do, you will take two things. One is upper bound, one is some initial, anything you can take care, some initial sparsity. Then for both cases, we'll do simultaneously, it will estimate what? One is support, one is channel estimation. Both will do. These steps will follow parallelly. Okay, this is one is correlation computation. Two choice means two for the two sparsity. You have to estimate support and we have to estimate the channel. Support estimation means it is estimating the detectable locations. Channel estimation means it is estimating the complete channel, right? Channel gains. While doing channel estimation, okay, so that you can detail find from this paper. Next, what work we have done is hardware software co-design we have developed for this method that recently get accepted in IEEE transaction and circuit systems 1 in this work. So what we have developed here, complete this structure. Yeah, this whatever we have proposed, it's hardware level how we are going to develop, and we have modified the algorithm also a little bit to make suitable for the hardware. What you have developed is that is computing some pseudo inverse. The pseudo inverse you can compute some different methods. One is SBD, one is QR, one is hybrid. Hybrid means both you are using SBD and QR. Three different methods we have used. This is the block diagram you can see here. Here this block diagram, if you can see. So here, you have the delayed of the location estimation, this part. Then is a coefficient estimation. This is update the coefficients. Everything you have there. First thing you have to estimate what? The locations or the support. Then you have to estimate the coefficient or the channel. Then you have to update. There is some iteration, some convergence. To converge it, there is some iteration will happen, that finally you will get the better one. So that then what we have done is, this is the basic flow diagram of the proposed TCSTP algorithm, or you can tell the hardware architecture. So this is how we have implemented on a PGA. We have considered here ZC706 Zinc SoC. So here we have done the complete, our algorithm will be done in the PGA, and the processor part, processor is core 1, core 2 parallelly doing two processing for the two thresholds. Because I told two thresholds are the two choice. So parallelly doing processing, so it will reduce the processing speed. These are some, you can see that these are some resource utilization for this proposed architecture. Okay, so here you can see that all the these are resources for the different techniques what I have shown. Accordingly you will get different resources here. So, and another one type of technology is known as intelligent reflecting surface. What is intelligent reflecting surface? If you many of you know this thing. So intelligent reflecting surface is given something like it has some planar surfaces where each of these planar surface is a reflecting surface. What will happen if you transmit some data, a signal will get reflected from here and received to the receiver. While reflecting here, some phase shift will be added with the signal. When you include some phase shift, what will happen that now you can program that phase shift. You can modify the phase shift. If you modify the phase shift, what will happen? You can make your system to be more reliable. For example, suppose your channel has a phase of suppose some theta, and you made here minus theta. So what will happen? This phase will completely gone. So what you will get? You will get total channel as it is. So you can remove the phase. Suppose some phase is earlier without using this RIS, you are getting, suppose your receive signal getting 0, but that you can remove it. That means the probability of deep fade, the scenario you can getting easily removed by using RIS concept or IRS concept. So here you are basically getting a beamformer gain that will give you better bit error rate. So and how you can remove that, controlling that, there is IRS controller which can be designed, and with knowledge of channel at the base station will give the information to the RIS controller, and it will be changing the phase shift. So accordingly, how so according to the objective function, that is a important point here. RIS related work, when you have to do, you have to be do many things, like you have to mostly focus on the two things. What is one? Channel estimation. One is RIS coefficient optimization. These two are very important point. In addition to that, you have to go for research allocation. All other directions are there, but very important point is RIS coefficient optimization. You have to optimize the RIS coefficient. So here I am showing that how we can club RIS with OTFS. If you're clubbing RIS with OTFS, you will get this kind of channel. This is the channel response from user to RIS link. So you, as you shown the previously, user to RIS. So you will get one channel from user to RIS, one channel response. Then another one you will get RIS to base station. Then you can make a cascade channel. So cascade channel response for the delayed approach signal you have to make. Otherwise, you cannot design the system. So this is how RF RIS to base station. Then finally, we will get user to base station. This is the direct link. This is the RIS to base station. Then these two are reflected. This is direct. Then finally, yeah, this is the cascaded one. Receive signal base station, receive signal at base station through RF reflecting element. That's it. This 41 expression will give you the complete system model input output relationship in delayed upper domain through RF RIS element. So then you can also write that expression in math vector matrix product, like HR. HR is the system. HR is the channel through. This is the, you can tell this HR as the cascaded delay Doppler matrix through RIS coefficient. So this 42 expression, this will give you the complete expression of input output relationship of delayed Doppler signal, X delayed Doppler transmit signal, YR is the delayed Doppler receive signal. So then you will get the point. Okay, this is receive signal. So okay, finally you will get receive signal if you have a direct path. So direct path plus reflected path through all reflecting elements, that will getting added. So final expression will be this. Okay, this is the, because what you can ignore also direct path, but here I have considered there is a direct path also. If you consider direct path, what will happen? The receive signal contains summation of both reflected and direct path. So that means you'll get a reflected paths here plus directed path. Okay, so now you can formulate any you can do research on this area. For example, there are many research areas on RIS coefficient. A very interesting research is channel estimation. It is no simple as the RIS OFDM that you can check. Okay, RIS or OTFS channel estimation is very difficult, critically when you are going for a highly time varying channel, because once you estimate the channel, meanwhile channel will be changed. So how you can update the phase? That's a very interesting important point will come, that while you're updating the phase, by that time channel is changed. When you transmit the data next phase, so channel is changed, you have updated the channel, updated the phase shift based on the previous channel, so you will not get that much of quality of service. Okay, so your objective will getting failed. So that's a very interesting challenging task of how to estimate the channel for RIS OTFS. Lot of people are doing paper, publishing paper, lot of assumptions, better lot of assumptions. Fine, we can have some assumption like coherence time or maybe little bit slow, but highly fading channel, it is little bit difficult. So you have to think learning based. If you can apply learning into this factor, so you can have a better channel estimation factor. Okay, some research highlights in our group we can show. One is I already told there is some low complexity linear data detection we have developed, and some lot of theoretical BER we have developed for OTFS, and some sparse channel estimation we have developed. RIS we have done also some work we have done, and RIS OTFS we have developed this thing, and some also we are going to work submit some new paper on RIS OTFS in this. And also few work we have done on the developing hardware architecture. This work we have published 2023, and one more recently we have published, and now also we have 24 we have published one conference SPCOM. Also we have developed MCOTFS. I told you this ISF15 SF50, that name is MCOTFS. It is multi-carrier OTFS. Another kind of OTFS known as a Jack OTFS, that is OTFS 2.0. So you can tell instead of doing these two steps, ISF50 and Heisenberg, you can directly do the Jack. So that is the next version of the OTFS. Interested people, there are many papers are there in Jack OTFS. You can study that. Okay, that you can develop channel estimation. And very interesting Jack OTFS case, the channel matrix structure is different than MCOTFS. And another point I would like to inform you that Jack OTFS, you have a two different kind of Jack. One is discrete Jack, one is continuous Jack. You can go for discrete Jack. Discrete Jack is more practically feasible. So discrete Jack OTFS, if you see that, so based on the filtering structure, your channel structure is getting changed. It is not similar as that of the MCOTFS. So that's why it demands lot of advanced algorithm, advanced techniques, equalization techniques, and so that you will get a low complexity things. Okay, there are a lot of algorithms. So next, let me complete it. So future research direction you can have, obviously you can use OTFS end-to-end transmission prototyping development, and as I told you, one kind of RIS with Jack OTFS you can go, and you can also go ISAC with OTFS. Lot of work has been done, but still there is a lot of work to be done. ISAC OTFS and AIML for the OTFS, it is not straightforward. You have to think how you can apply the AIML for the OTFS. And another okay, let me complete these things. I have few references. So I have shown also our papers. In addition to, you can follow many papers. Like this is a simple paper, but you will get this six reference. You can get a lot of idea, a basic idea how you can give a OTFS complete transmitter receiver structure for an ideal scenario. Okay, then you can catch the later on things. Whatever explained, how you are getting the block segment structure. That explanation you can get more detailed manner in this paper. After that, you can go many our paper, this paper, or whatever I have explained, the sparsity paper or the hardware software. Also recently some paper has been published, so you can go that. You can go the detail of OTFS, how work has been done, and also RIS, ISAC. So interested people, you can club OTFS with many interesting technologies. Okay, thank you for this talk. Let us, if you have any questions, I will be happy to answer those. Any questions, please?
So I request participants, if you have any queries. So unmute yourself and So you can raise the hand if you have any queries, and if you are unable to ask the question, let us know. If your mic is we're unable to.
Yeah, mic is enabled. You please directly can ask the questions.
Okay. Share the screen or someone asked what? Share the screen or share the PPT?
They are asking to say the PPT.
Okay.
So just to add, sir will happy to share his PPT if he will receive 2-3 questions from participants.
Okay. Sure. In MATLAB, someone is asking in MATLAB which toolbox has been used for channel estimation, or what you're asking?
Which toolbox need to be used for channel estimation?
Channel estimation toolbox, you can write code yourself. Channel estimation means what? You have to develop, first point is you have to design a transmit frame. What kind of channel estimation are going to be? So generally more conventional manner is you have to transmit some pilot symbols. So pilot symbols you transmit, then which channel estimation you are going to use. So you can use like least square, there is more basic channel estimation. So you have the pilot, you have transmitted, so you have received signal. So basically you can develop a transmitted signal, sorry, pilot signal into inverse into the received signal. So then you get the channel. So this is a very simple step of the channel estimation. So what kind of channel estimation you are going to develop? You have to write your code, and there is existing Simulink. Simulink you can have some estimators, so that you can use. But accordingly, you have to the transmitter side you have to do some, but that is existing blocks. So better not to use existing blocks. Better to write your own code. So then you'll get idea how channel estimation will be done. Otherwise, you will get a black box. Like you have a transmitter frame, pilot frame, transmitter frame, everything will be there inside the block box. And the receiver you have channel estimation toolbox. You will use that one. So you'll not get any idea. You have to write basic attendance. Okay. How to do Monte Carlo simulations? So Monte Carlo simulations means what? You have to do iterative manner. So one channel, that means you have to generate a for one within one loop. What you do, you generate transmit signals, right? You generate one channel, a random channel. Basically, you generate a Gaussian channel. You write rand n, that thing, complex Gaussian channel things. Then what you do, then you do channel estimation, transmitted channel estimation, then you equalization, everything you will do within one loop. And that equalization once you do, then what you have transmitted, the data, that you compare it, how many data are being correctly received. So you mark the error. So then you repeat this per 1,000 or 10,000 type of manner. How many repetitions you will do, that is roughly what BR you want to find. So accordingly, suppose you want to get 10 to the power minus 3 beta rate. What you do, 1 by 10 to the power minus 3. That means 10 to the power 3 times you have to do the for loop. Then you get that. Right. Okay. So like that you can do. There is Monte Carlo simulation. And there are no more questions, I think.
Uh, Professor Himanshu, I have a question. You have done that is hardware software co-design.
Yes.
That is on ZCU 706.
Yeah.
Right. So is it based on ISFFT based OTFS or?
Yes. So what we have done is, here we have not done end-to-end system. What we have done is, we
Okay.
have done the estimator part we have implemented.
Okay. Okay.
Yeah, end-to-end we are doing. So transmitter block we have completed almost. Receiver is remaining. So receiver one, channel estimation part, this one is completed. That means complete things we have done. Students have been done in very long. They have written completely.
Okay.
Yeah, they have.
Actually, one of my MTech student now he has done the transmitter part of the OTFS in that is what we call jet board. He was able to get the transmitted signal and he could match with the MATLAB simulation. In that is, he has used the IP course to design that.
So he's
So we can.
implementing Vivado, or Vivado he is doing, or what he is doing?
Yeah, Vivado.
Oh, yeah.
So he has written a code in Verilog and he was able to get the transmitted signal. He is now working on receiver part.
Okay. So he can do receive very simple manner, like some basic channel estimation technique. You can take basic one is embedded pilot, but what you will do, don't use the embedded pilot structure completely. You can do what, remove the everything, like only take only one pilot. Okay, yeah, assume that channel is constant. He's doing slow fading channel, so assume that channel is constant. First, he can do one pilot, one OTFS frame, only one pilot, remaining are zeros, and estimate applying the threshold technique. Estimate the channel along with the gain, along with the locations. So you will get the, suppose there are two delayed of the locations. Okay, so you can easily estimate that locations along with the gain using that method. So he can follow embedded pilot method, but don't follow exactly that structure. He remove all the data
Okay,
and
okay.
only for the pilot, remove all are the zeros. So then he will be easily he can do. Then once you got the channel estimation, then next frame you can transmit complete data. Since you are working on trading, so what you can assume that first one is that is a valid assumption. First frame contains pilot only, next frame data, then pilot, then data, then pilot, then data. Like that only he can do. So this is a simplified
Okay.
manner he can do, and he will not face issues.
Okay. And there is a one question here. One is, what are the challenges in India for 5G and 6G spectrum? Nowadays, huge number of users are used mobile phones.
Challenges, many challenges you will get, like, so how, in the sense of cognitive radio, one challenge, like how to get means perfectly use the spectrums, right? That is one thing you can accommodate, go to the terahertz, or suppose you are using FR1. Many mobile phones using means basic things, what you get, high data rate, right? Spectral efficiency, that is one point. Then only you can use. So more spectral efficiency, how you can get? So one is your RIS. RIS can give you the higher spectral efficiency. Then you can get, and you can use your spectrums very efficiently. And after that, you know that how the spectrums will be allotted and all these things. That will be separate thing that you have to study on the detailed manner. How will you allocate the spectrums? But in wireless system design, I can tell that only you have to focus the spectral efficiency as a physical engineer. Then spectral efficiency will going to higher, then data rate will be higher. So go to, so how can do, you have to think in physical layer wireless system designer perspective point. So your MIMO, massive MIMO, RIS, these technology are coming. So now there massive MIMO, that is known as what is all higher version of the massive MIMO also rating, higher number of antennas. So that can be used at the base station to get the better. So that is also 6G it is coming, na, higher number of antennas. ISAC is that advantage things. ISAC is coming, but that is something else. But based on the question is how to efficiently use spectrum. What I can understand. So spectrum efficiently you can use if will spectral efficiency going to be higher. So that you can get by massive MIMO is one point existing what we have. And RIS that is did not came till now, na? So if we'll get that is better, much better you will get.
One more question. There is a which type of
MATLAB will be drone. That I don't know actually. Drone I have not
okay.
worked, so I don't know which kind of tools you can search. MATLAB drone. See, drone if you are going to communicate, that will be. I think there is something like FSS, right? Frequency space spectrum. That is. I think they are not using well. They are not using. I think they are using some Bluetooth link, but means people are doing in the like they're doing in drone, but I don't have that much of idea. You can ask some who is working on the drone, or they can answer you better. More
One more
questions.
question. It is believed that OFDM is a modulation scheme which is considered to be freeze for 6G. So how would be the chance of OTFS now, as the 3GPP has freezed it as OFDM as
Yeah,
the modulation scheme for
see,
6G now?
yeah, that I understand. 3GPP has taken WebDM. Main reason is no one going to remove WebDM because of that complexity. The one-tab equalizer I told now, that is something we cannot get by OTFS. So that
Okay, okay.
another thing is that if you are going to replace everything mobile cost, what will happen to the companies? They cannot bear. So it will come, but it will not completely replace. But what I think that it will come for some particular applications that people are working on this. Like DRDO is working, ISRO is working on this. They will give for some particular applications. And one more
Okay.
interesting I can tell in the sensing. Sensing OTFS give more accuracy than OFDM because you get in related upper domain na, so you're getting better accuracy. So in sensing you can use OTFS. So it will cannot replace completely OFDM, but for some particular use cases OTFS will come. That will come this.
Okay. Okay. Mm. Okay, thank you, Professor Himanshu, for a nice, very exhaustive lecture and very intuitive and very deep explanation on OTFS and related area, and also including RIS and how it is implemented in mainly the FEJ. So, thank you very much for your great lecture, and we are very grateful to you. Thank you. Thank you. So, dear participants, our next lecture will be starting soon by Dr. Pallab Maji. So, we'll be continuing with the same link for the next lecture. Pallab,
Sir.
you are available now?
Yes, sir.
Yeah. So you can share your
Hello, sir. Can you hear me?
yeah. I can hear.
Hi. Hello, sir. Very good afternoon. Very good evening.
So can start. You will be. You can check whether you can share it, and then I will introduce.
I think I can share.
Okay. Dear participants, once again welcome back to the that is second session of the day 2. So Dr. Pallab Maji, briefly, is a
Sir,
very
sir,
yeah. I'm
sir,
audible.
I may need to rejoin.
Okay.
Just give me a minute. I'll rejoin. Yes, sir. So can you hear me?
Can I, Dr. Pallab?
Yes, sir. Can you hear me?
Yeah. So, dear participants, we'll start the next session. So, briefly, I will be introducing Dr. Pallab. He's a automotive technologist. He completed his BTech from Bengal College of Engineering from 2004 to 2008, and he completed his MTech and doctorate from NIT Rourkela in 2011 and 2016 respectively. After that, he joined the that is Wipro as algorithm developer. Then he worked for senior technical lead in the Mercedes-Benz Research and Development India. Then he also worked as a senior solution architect in deep learning, NVIDIA. Then he also worked in Ola Electric, and presently he is a founder and CEO of Gahan AI Private Limited, where he develops the autonomous vehicles. So I welcome Dr. Pallav for his next session, and he would be presenting his lecture on joint radar communication for autonomous vehicle. Thank you, Pallav.
Thank you so much, sir. Hello, everyone. Uh, Sir, how is the format? Like, can I get take questions during the session, or should I wait until the end?
You can do anything. You can do at the end. It would be good.
Okay. So, yeah, thank
If
you
they
so much
ask
for the
in middle
wonderful.
also, if you can able to do that, it's okay. And would
Yeah,
be better,
sure.
I feel.
Yeah. So, I hope you can see my screen. Sir,
Yes,
Yes,
sir, it is
yes.
visible.
is my screen visible? Okay. Yeah, thank you. So, hello everyone. Good evening. Oh, sorry. Yeah, I'm having some issue with my uh, system. Just give me a minute, sir, please.
Okay.
I don't know. There is some issue with my system. Is my screen visible?
Yes, yes.
Yes, sir.
Sir, do you know how to stop this presenter mode?
I have to stop it. You want to stop from presenter mode
Somehow the presenter mode is getting activated by default.
because you are going to present, so it is a presenter mode. Otherwise, you cannot present.
Okay, okay. ठीक है. Actually, I had some notes also, so but that's fine. Okay. ठीक है, sir. I'll get started with that. Please. Okay. Hello, everyone. Good evening. Sorry for the initial technical issues. Uh, Thank you so much, sir, for this wonderful introduction. Really appreciate the words coming from you. Uh, so, just for everyone, Seychelles sir has been guiding us mostly from like almost, I know him from over 10 years now. So he has been guiding us across multiple domain, and whatever we have learned, there is a huge contribution from his side as well in the places that I am I have been working. So thank you so much, sir. And today, I wanted to talk about joint radar and communication, specifically focusing on autonomous driving and on the industry of automotive, how it is actually with the next wave of innovation and why it is making so much of R&D, so much of research and innovation is going on, and there are like plenty of resources that are plenty of companies who are pouring in huge amount of resources. And for most of us who are into this field of signal processing, wireless communication, and so on, this is actually something where lot of R&D efforts are going in, and there we see lot of important innovations around this. Now, coming to some of the key things that we are going to talk about today is we are going to talk about what automotive domain is all about, and why sensing in automotive domain is very important and crucial. But at the same point of time, with more and more vehicles coming onto the road, as we see the traffic densities are growing higher and higher, we actually see a lot of scope for communication between these devices or these vehicles, which can result in multiple different use cases and applications that can improve the business and can improve on the quality of the services that we are going to give to our customers. And with that in light, uh, we as a company at Gahan AI as well are heavily investing in this section of joint radar and communication. So now coming to joint radar and communication, basically what we are now talking about is two different concepts. Just a quick, so I'm following the chat as well. So uh, as a quick, yeah, if you can uh, tell me how many of you, you can just raise your hands. How many of you are aware of how a radar works? A typical automotive or any kind of radar, how they work? Okay, I see a lot of hands going up. Yeah. So a typical way in which we work with radar is that it, the full form of radar is radio detection and ranging. So that means we actually throw out a radio beam out in the world, and then that radio beam goes and strikes some objects and then returns back. Now, based on the way they return back, we can actually figure out that where that object is, which direction that object is flowing, which direction the object is moving, with how much of velocity it is moving, and so on and so forth. So it's a very it was one of the first uh, sensor that was being used in automotive to do lot of object detections, and and many of your vehicles today, even in India, are using this technology, and it is widely getting popularity in Indian ecosystem as well. You would see nowadays lot of vehicles that are coming with ADAS or driver assistance system, typically are dependent on radar and camera as a sensor, where radar plays a very important factor. Why do we use radar? Because of robust weather conditions. Let's say, for example, in north of India, and even in the central part of India, if you see, there is in these in during these conditions, there are huge amount of fog or smog across different states, and because of that, when there is huge amount of risk in or huge amount of accidents that happen during these conditions. Now, if you apply if you use a camera for these for detection of objects in these kind of conditions, cameras does not work because of the limitations in the physics of the whole sensor. Camera depends on light as a medium for detection, right? Light disperses in fog, so it cannot see through fog. So you cannot have a camera that can actually see through fog. But under but if you replace that, or if you have an additional radar, then the radar can actually see through fog very easily. Even when it is raining heavily, or even in areas where you have pitch darkness, in those cases also radar can actually see quite far because it is dependent on radio waves. Now, if you see the frequencies, there are different types of radar, but mostly automotive radars are in range of 24 gigahertz, 60 gigahertz, 77 gigahertz, and so on. And because of these frequencies, there is a huge penetration of these radio waves across different types of weather conditions. And that's why radar is actually used for many of these ADAS applications. The other important advantage of radar is that it can detect an object and give directly the velocity of those objects. Now, when we develop these kind of applications, let's say, for example, adaptive cruise control. In adaptive cruise control, what happens? You actually throw in the electromagnetic beam, and then you get lot of information about that vehicle, and you get the vehicle speed or the velocity as well. Now, based on that velocity, we need to calculate something called as time to collision. Time to collision is nothing but Newton's second law. If you apply, you basically get your velocity, the relative velocity between the two objects, then you or directly know that at what point of time two objects are going to collide. So based on that, you can either accelerate or you can brake. Right. So that's essentially is what adaptive cruise control. And this can, without much computational prowess, we can actually implement this through very small microcontrollers just using a radar as a sensor. So, yeah, so these kind of applications see huge, huge impact from introducing radar as a sensor. So radar as a sensor has been there for a long time, and even in Indian ecosystem, the ADAS systems are implementing or are being developed through implementation of these automotive radar. We as a company, we have also we are proud to announce that we are one of the few companies who have actually built an automotive radar. Now, why automotive radar is little bit difficult to build is because of the power restrictions. Here we cannot just pump in a huge amount of power, because as you know, the distance. So if you see the radar equation, the distance is actually a is exponentially proportional to the power that it is required. And because of that, if we want to get to a distance of say 200 300 meters, then often we have to work at a very low power, because in vehicles, mm, there isn't huge amount of power isn't available. Like there doesn't exist an AC socket where I can actually pull in as much as power I want. I cannot do that, right? So that's where automotive radar development is quite difficult because of two things. One, it needs to be very power efficient. The second thing is that it needs to be also encapsulated into a very small form factor. It cannot be a huge, it cannot have a very huge antenna. So the aperture of your radar cannot be huge. You basically have to work with smaller antennas. So in most of these cases, these are the constraints under which we need to build the radar. Now, when we are building this kind of radar, and as I said, the other side of it is that we are just sending electromagnetic waves that goes and strikes other object and then comes back. But inside that electromagnetic wave, there is no information that we are encoding. Now, let's say, for example, I need to broadcast to a few other vehicles around my surrounding that I am low on, uh, let's say, fuel or low on energy. It can be an EV vehicle or it can be a diesel or any other gasoline powered vehicle. Let's say you want to broadcast that, and if there is anybody who in the surrounding driving within that highway can actually help you, they can communicate back. We can easily implement these kind of applications because I already have a radar which is emitting electromagnetic wave. So now if I can actually make that radar also encode some information within that signal and then transmit it to the nearby vehicles, and if they have a receiver where they can receive it, then I easily can achieve a V2X with no additional cost in the hardware, right? So if we are able to do that, then my V2V communication basically gets sorted out. Now, the challenge over here is that how uh, how do we merge both of these together? Because in one side we have the radar, which actually is going to send the signal and it is going to sense an object. But if we can, but if we en but within that, if you see the way radar propagation actually happens, within that encoding a signal becomes really very difficult. Now, if we now how do we achieve this? That's what we are going to discuss together in next half an hour, 45 minutes or so. As I said, the dual function actually brings in lot of advantage, and this is where we want to combine all of these because, as I said, we reduce on the hardware. We can actually use antennas for share the antennas and the spectrum. We can also get lot of other advantages in terms of applications that we can build using the same hardware. So we can reduce the cost overall and so on. So this is a win-win situation, but it is easier said than done. So essentially, the challenges that we are facing is that, as I said, we cannot emit a huge amount of power. So, and if we emit huge amount of power, then it has some adverse effect as well. So mostly the detection that we do in radar, it is around hundreds or 200s of meters for automotive. Of course, there are radars which are implemented for different type of applications where you get kilometers and kilometers of range. But in automotive radars, primarily 200, 300-meter is considered as long range radar detection systems. The second thing is the second challenge is that the size constraint. We have to have a very small envelope because we do not get huge amount of size and we cannot have big antennas placed within the vehicle. Of course, limited power budget is one of the key issues. So these are the unique challenges of developing an automotive radar. Now, I will be using these terminologies in different ways. So DFRC or dual function radar communication or JRC, joint radar and communication. Essentially, they are pretty much the same. It's just the terminologies are different. It's just that the acronyms are different, but they basically mean the same way. So there are essentially four different strategies which we can actually use for these kind of applications. So the first one is you basically have So we will double click on each one of them. But here, as you can see, you basically have two different systems clubbed into one hardware piece where you have a separate communication signaling system which actually connects with different types of communication infrastructure, and then you have a separate system which actually does the sensing, which is through the radar signal processing. Now in here what happens, you basically uh, based on the analogies that I have given, it essentially means what? You are actually taking two different hardware and mixing them together into one hardware box. It's not really a joint performance of radar and communication. It is basically like two different hardwares stitched together to perform two different functions, but enclosed within one single module. It's as good as like that, two different systems. The other side then comes in that when we talk about these kind of signals, if I want to do radar communication, and if I want to do them together, then the nature of the system is that whenever I actually increase on the sensing accuracy, at that point of time, I basically cannot have a very high bit rate of data that I can transmit. And if I transmit a high bit rate of data at that point of time, the sensing accuracy actually goes down quite a bit. And that's the trade-off which we need to balance. So now what is happening in the figure B and D, as you can see, we are primarily having either radar as the important factor or as the primary component, and then communication is just a secondary component. Let's say, for example, we can just throw a radar beam and then encode small information within it and transmit it. Or we can actually have a very good communication system, and then we just have some way of finding out within a fairly low accuracy, we can actually find out roughly around which region that particular object, or localize the different type of objects. The best case scenario would be if we can actually have a single system where the communication data rate is also quite high, but at the same point of time, we can actually do a very good detection as well. So that is the sweet spot which or that is the aim that we are looking how can we get to there. And that's where, if you see, for a system, let's say if our task is to actually do a V2V and radar based detection, that is what at Gahan AI what we are trying to achieve. So a radar which can actually be which can actually encode good amount of information that can be relayed onto the rest of the vehicles around the ego vehicle, and at the same point of time it has a very good high accuracy as well. On the radar side, the accuracy is very important and imperative, because safety critical systems like driver assistance systems depends on that. If my detection accuracy goes down, then suddenly it becomes critical and it becomes very life threatening for someone who is driving that kind of a vehicle. At the same point of time, if I am providing a communication system which needs to relay some sort of essential information across different vehicles within that range, I need to be very accurate with that as well. So that is what we are trying to build at Gahan AI. So as I said, the initial way of doing it, the strategy one, which is coordinating separate signals. It is like two different types of signaling system. One specifically doing radar detections, and the other one doing the communication system. And how do we do that? We can either have a time division multiplexing, where we should be able to have different frequencies and different systems running within the different time specifically allocated for that. Now, this the best part is that we are not actually doing very we are actually not either focusing more on the communication or focusing more on the radar. We are not doing that. We are equally providing each one of these systems proper weightage. But the problem is that because the resource allocation optimization, and we are doing like time or frequency based time frequency based division across, the problem that starts coming in is that the latency of the systems grows higher. The or to counter the latency, then we have to have a bigger hardware. Now, again, going back to the same problem, we cannot have a very big hardware. At the same point of time, we cannot have very high latency as well. So essentially, this is something which is not a very good strategy for these kind of systems. It can be a good strategy where power or size and cost is not a very high priority. In those kind of cases, these kind of systems coordinate, which is based on the coordinated separate signal strategy, can actually work quite well. The strategy two is where we actually give higher weightage to the communication, but we limit the radar, we limit the sensing performance. So in that case, your your communication signal processing exactly remains the same, like how you are doing. You can use an OFDM communication based system and use that same electromagnetic wave that you are transmitting. You can use that same thing and see how much of it comes back. And once it comes back, there you need to now figure out that how much of phase shift and how much of uh, um, uh, frequency change that is happening, and based on that you can find out where the particular object is located, and based on the phase shift you can actually figure out a good you can figure out a good accuracy with the speed as well. But now comes in the problem. The problem is that whenever we have these kind of setup on the receiver side, we actually require a higher bandwidth for a better range resolution. So imagine that there are two objects which are moving at a distance of 1 meter apart from each other, or there are five objects which are moving little bit away from each other. All of these things will somehow get clustered into one object or one detection. You won't be able to decipher between multiple objects. The reason behind is that the range resolution is much lower, because when you are doing OFDM at that point of time, the bandwidth that you are applying for individual channels, that is quite limited. Right. So that's where you require a very high costly wideband hardware, which is again, it is not only about the cost, but at the same point of time, you will require a higher power. You will require, and when there is a higher power, you require active cooling and all these kind of things. So the system becomes bulky. The system becomes really very difficult to install, maintain, and so on. And at the same point of time, you are not going to get a very good accuracy at all. But it can actually work as a very good communication system. Am I audible?
Yes, yes.
Okay. I see my
But I
video got.
think participants
I somehow see my video got
stuck.
stuck. Is it working fine?
Yeah, yeah.
Okay,
We are
good.
in the video WebDM strategy 3. Yeah, yeah.
Hmm. So I'll just go to that. Thank you, sir. So ideally, what happens here, you are getting a very good, very high data rate, and you can actually leverage a lot of the existing ecosystem of the hardware, because most of these hardware are based on the IEEE standards, and there exist lot of uh, 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 low cost hardware as well for this. But when we are putting it for sensing, at that point of time, somehow this doesn't work very well with the kind of accuracy that we require. So this is not a strategy that we can actually apply for an automotive domain. Again, this strategy can work very well for other applications where communication needs to take the high priority, but the sensing can have relatively low accuracy as well. In those kind of domain, it can work very well. So again, as I was saying earlier as well, there will be lot of issues, primarily because of the range Doppler. You cannot actually couple both of them together, because if you see how an FMCW radar works, because of the change, so we need to figure out where exactly the phase shift is happening so that we can figure out the right range resolution. We also need to see how the frequency is changing. So essentially what we do is we actually have a chirp signal, which is like a frequency modulated, and because of that frequency modulated, we require some amount of bandwidth based on which the frequency is modulated quite a bit, so that we get a very good range as well as a Doppler resolution as well. But that is something which we cannot afford to do if we are using an OFDM signal. So this is the main problem. Now, how do we change that? If there is another kind of a propagation that we can form, which can allow us to do the FMCW way of ranging and detection, but at the same point of time, we should be able to add more and more information, pack high amount of information. That is something which we are again looking for. So under the same context now, when we talk about radar waveform based system, here what happens, we have, as I said, most of these radars that we develop are based on FMCW waves. And in that FMCW, it stands for frequency modulated continuous wave. So it's a continuous wave where we are modulating the frequency. So if you do the frequency plot, what you will see is that there is a linearly rising edge, and then that is where we actually talk about these radars which operate between two range of frequencies. Let's say, for example, we have developed two radars which works between 77 to 76 to 77 gigahertz. This is a permitted range by Government of India for automotive applications. But then there is also a discussion for a better range resolution and better velocity resolution, where we are working between 77 to 81 gigahertz. This is still under draft and it has not been approved by Government of India yet. So mostly what we do is we vary the signal between these 2 points, and we keep and that is what we call it as the chirp signal. And you can see now we are actually talking about a huge amount of bandwidth that is being done just for only sensing. Right? So to convey these data, we can do few things. So to pack some amount of data within that, we can actually do few things. But again, there the trade-off is that we can only decode so much of information, not a huge amount of information is what we can decode within that signal. So because of that, essentially our that's why the name is radar waveform based, where the radar is actually the waveform is defined in such a way that we can do. I will show you one example as well, where we are using two different types of systems, where we are able to actually do some kind of index modulation to figure out that how we can transmit small amount of data. However, the data transfer is in kilobits or in lesser tens of kilobits around that. We cannot get more than that. So the whole idea of index modulation is basically based on the different indexes. As it is multi-carrier based, we can actually combine and we can do a carrier selection for different. So within this frequency also, we can actually have different types of data encoded within that index modulation so that we can use to transmit them, and that being on the other side received, and we can decode them. But then that formulation is actually quite that does not formulate a huge amount of data bit rate or the data bandwidth as well. Yeah, I was seeing few hands raised in between. Is there any question? If there is any question, you can type it on the chat as well.
I think it was previously raised a question. And
Okay. So if you can put your hands down. So if there is any question from anybody, they can put their hands up. Then I will try to respond to them. Sir, is there a way that we can make everybody put their hands down?
uh, I think that option.
Okay. ठीक है, sir, no problem. Okay, now coming to the coming to the IMFR based system architecture. So this is a hardware which is being modified to design. This is from a paper. This is not our work, just for a reference. I have put the reference of this paper in the chat as well. Is my presentation changing?
It is in the index modulation. Hello. 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 हेलो हाँ पल्लव
I think maybe यहाँ पे internet off हो गया था. I could not get. I am joining that.
हाँ ओके
Hello, sir. Can you hear me?
Hello?
Yes, sir. Can you
Yeah.
give me
Hello.
the sharing presentation rights?
How?
Yeah. Yeah.
Yeah, now you are able to get it.
Yes.
Yeah.
I hope you should be able to see my screen now.
Hi, yes, yes.
Yeah. Just give me a minute. Yeah. So here, this is basically a system where you can actually, this is again based on a paper. I have cited the paper at the end. You can refer to that paper as well. It's a very good paper on the different types of joint radar and communication systems that are applied on automotive specifically. Here, what we primarily is, if you can see the image, what basically this experiment does is, here there are four different subcarrier sets. We cannot have more than them because of the differentiation in the chirp frequency, as I said. So based on that, they have used four different types of subcarrier frequencies, and each one of them, they primarily are used through a MIMO antenna. And based on that, we actually have 3 bits of information that we can share, uh, 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 that we can actually go and share simultaneously. And this is the mapping rule. So as you can see, if we want to do a very good perception or sensing at that point of time, the amount of bitrate that we can actually transmit is quite low. And this is an example of that. We will go through one of our example as well in some time, which we have done some simulation and some hardware on that. The third one, which is currently where the fourth strategy is where we are currently trying to formulate, is a new sort of joint waveform design that can have the capability of doing both the radar sensing as well as the camera based, as well as the communication based signal processing as well. Now, the concept is that if we can have a dedicated waveform or a strategy or a design which can be optimized for both radar and communication simultaneously. So it cannot be a conventional signaling. It which already we have seen, as you saw in the last example as well. If we are trying to use OFDM as a OFDM based communication and implement within the radar sensing paradigm, then it is not giving us very high data rate. So it cannot be any kind of a conventional signaling method. It has to be optimized for this dual function, and the controllable performance has to be there. Like, we should be able to have a good balance of both sensing as well as communication, a high data rate communication as well. So so the current limitations, as we say, the challenge is a good range resolution and a Doppler velocity resolution. So on the range resolution, if we are actually using similar type, we need a very high bandwidth of signal to have a proper distinction between multiple objects which are moving at different velocities and but are very close to each other. And that point of time, the range resolution comes into the picture. Along with that, we also need to have a variation of frequency which can be detected. The change in the frequency can be detected so that we can figure out what is what is actually the relative velocity of those fast moving vehicles as well. Normally, if you see in an automotive application, the velocity that we are expecting for the detector, for a good detector which can work in any of these ADAS systems, needs to have at least 140, 150 kilometers per hour or higher. But at least we need to have about 140 kilometers per hour as the relative velocity. Now, that's a very big challenge. And at the same point of time, for a long range radar, we need to have a range of at least 150 meters or above. So that's actually a very difficult task if you use the current generation of signal processing and the current generation of communication signaling that exists. If we want to apply the first strategy, which is like two separate individual systems, one doing communication and one doing automotive sensing, which is currently how the systems are being implemented in today as we speak, that's that is going to have a higher computational burden. So it is going to be very high computationally expensive, but at the same point of time, it is going to be very power hungry as well. So it's still a emerging technology. There doesn't exist a silver bullet. Please take this with some pinch of salt, that there exists some amount of improvements that we were able to do as a community, but there does not exist a solution yet on this which actually does both of them very well. So yeah, again on the same paper, if you see, you have in one side IMFAR, which actually gets a lot of interference on the communication side, but does very good sensing and detection. But on the other side, when you apply OFDM based communication, at that point of time, you get a good data rate and you get a good uh, uh, a very good communication system with very high accuracy and very very high signal to noise ratio. But at the same point of time, you actually don't get a very good range resolution from your detections as well. Yeah. So currently what we are trying to do is we are trying few approaches. One of the critical approach that we are trying uh, is based on the uh, have you guys heard of something called as synthetic aperture radar? Yeah. So when you talk about the synthetic aperture radar, what exactly it does is the aperture is something which actually shifts, and based on that, we get a so there is a uh, uh, there you primarily get multiple resolution of image imagery through the electromagnetic wave that is being transmitted, and then you stitch all of them together to get a better view of the or get a better insight about the imaging that you are trying to do. In the MIMO radar also, a similar type of technique can be applied, which is called as virtual aperture. In the virtual aperture, again, the same concept, but rather than having two different types of uh, mm, hardware, applying two different types of uh, uh, transmission. Here the here the antenna system and the processing remains exactly the same, but for within that different virtual aperture, the uh, the contents or the parameters of the signal that we are transmitting, that gets changed without any additional hardware. So it is mostly because of the different types of software defined radio concepts that have come up, and at a lower additional hardware architecture, we can actually develop lot of these ships which are driven through your software. And that's where we have made some progress. And I will show you something that we have recently done at our lab as well. On the other side, there is another approach where we have actually already done two different type of radar which operates in the band of 77 gigahertz. And there we actually have different types of so this is again coming in from another paper which talks about the de-chirp recovery. So the de-chirp recovery exactly means that we are about if we already know. So let's say, for example, in radar, we apply, as we discussed earlier, we apply frequency modulated continuous wave, and that's a chirp. That is something which is known that it will go from 77 gigahertz to 81 gigahertz in our case, and it will have a different type of slope based on the number of chirps that we are generating within a time period, and the uh, uh, amount of time that we allocate for individual chirp. But that slope is going to change, but the uh, frequency modulation is going to remain the same. Now, if we can actually have a variable chirp, and if on the receiver side, if we can extract out that the first chirp or the second chirp had or individual chirp can be assigned. Let's say right now we in our radar we provide within a time period we have 128 chirp samples based on which we do the detection. Now, each one of these 128 chirp samples, if we can have assign a particular symbol based on the different types of and that on the receiver side, if we can decipher them or de-chirp them, then there is a possibility that we can actually send within that sample period, we can send 128 different symbols, and that can immensely raise the bit rate of our transmission. But this is something which is very difficult to do, because how do you know that which chirp you are sending ahead of time on the other side of the receiver? So this is something which we are trying to work on. There are some predefined strategies which has been proposed, but this is evolving to be a very solid area of research. And these are the two major area of research where we are banking. There is also another perspective from few researchers that we actually use the same hardware, but we have two different bands to that, and that can be very easily enabled through different type of antenna patterns on the patch antenna designs. But somehow, so you basically need a patch antenna which has two different types of frequency responses. If you are able to get that, let's say one at 24 gigahertz and one at 77 gigahertz, then you can use these two as a different for different purposes. But that's something which is not being actively, or that is, so many people have tried it, but that somehow is very difficult to achieve, and there are a lot of shortcomings in that.
Pallab,
With
they are saying that slides are not changing. Is it same slide?
key automotive radar requirements,
Okay, okay.
this is the slide.
Yeah.
Yeah, I'm talking about this. So
Oh,
this is the wave operation which I was talking about. So there are approaches where you, as I said, the frequencies that are allotted for automotive radar are 24 gigahertz, 60 gigahertz, and 77 gigahertz. So these are allowed frequencies where we can actually use them for radar applications in automotive. And within these frequencies, there are like you can have compact patch antennas which can enable two bands simultaneously, and then you can actually, but at the end, on the back end, then you need to have two different hardware, either same hardware being time multiplexed, or the same hardware, or you can have two different hardware transmitting through the same antenna array. So there are these kind of approaches. We are mostly invested into the second and the third one. So yeah, again, this is something which we have already discussed. Uh, there are a lot of again, one of the challenge I just wanted to highlight that is, apart from also designing these kind of radar, we also have lot of challenges within the ecosystem, and this is something which many of the students and university academia people can actually help the industry, is on the real world testing side as well. Lot of these testing equipments and the testing scenarios becomes really very challenging for a startup or a small company who have limited resources. And that's where we many of these companies like ours, they like to collaborate with lot of universities where the technology as well as the R&D side uh, on and the testing side can also be jointly shared. And one of the reason why uh, our company and with NIT Rourkela also we are connected, is that with NIT Rourkela we are also building something similar, and we have already got a project which we are working with Professor Hiramat and with Professor Maiti from the ECE department, where we are developing around, we are actually doing the research around these spaces that I talked about. And this is something which might be interesting. If you already have some kind of a testing framework, you would be able to work with many of the industry and build something which will be useful for our country. So yeah, these are just some of the things that what we intend to do. So this is one of the JRC system that I was talking about. This is something that we have recently we have recently tested, and we were able to, as I was saying, we were able to use the D-chirp method, where, as you can see here, we have a 77 to 80, 77 gigahertz a system. Our radar operates at 77 to 81 gigahertz, but we used a bandwidth of 100 megahertz, and we were just trying to get up to a range of 10 meters. So we had a corner reflector which was placed at we had multiple corner reflectors which were placed at a distance of 10 meters. In this case, we used I think 3 corner reflectors around the same, just so that we can maximize the return signal higher, so that the uh, there is lesser loss. Of course, this is very preliminary experiment, and we were able to actually figure out that we at a range of 10 meters we were able to figure out the uh, we were able to figure out the object. At the same point of time, we were also able to do a BPSK based data transmission, and we are trying to go into a higher data rate or a higher communication system, something which is actually in real world can be useful. We understand that this is not going to be enough as of now, but we are just trying to implement the de-chirp mechanisms as much as possible, so that we can build the base, the foundation, and then increase on top of it. And here, as you can see, we have the different chirp indexes on the top, and based on this we are trying to extract out. This is the block diagram of the system. So there are 2 different paths. One is on the range Doppler path, which is by default straightforward, but on the other side the data recovery path is where the communication processing actually happens. That's where the de-chirp mechanism comes into it. So these are the 2 receivers. So we had the so we had because this HackRF has only one transmit channel and one receive channel, we were able to use it. So that's where we had to make 2 of it, and we were able to do this experiment. So, yep. So that's primarily what I have for today, sir. If there is any question. Hi. Is there any question?
Participants, let us know if you have any questions. What waveform is used
with HackRF? So currently we are actually using so waveform is basically a chirp frequency that I was talking about, but with a different. So for each one of the chirp, we have a different slope assigned to it. So it's not a standard waveform, if that's what you are asking for.
So he's asking question like, what is the
frequency? So currently we are testing in between. So on the HackRF side, we are actually testing it within 2.4 to 3 gigahertz, within that span, but we also have another hardware. Unfortunately, that hardware is currently in process of getting patented, so I cannot show you the photo of that. But but I can. But we have designed it with a TI chipset. We have designed it with a TI chipset, which is based on an 1843 AWR 1843 chipset, and that's the hardware on which we are going to implement that. But on the HackRF, it is between 2.4 and 3 gigahertz. Any other questions?
So any other questions from the any chance of sensing? There's a question like any chance of sensing by LT or other waveforms from base station?
Uh, Sorry, where did it go? Sorry, sir. Oh, there
There
is
is
a
a
question.
question like
Any chance for sensing by LT or other waveforms? Honestly, I am not very sure about that, because all the waveforms, out of all the waveforms, you have OTFS, you have OFDM, and you have, let's say, for example, FBMC, all these kind of waveforms. Most of the literature they have already tried out. I have not personally tried out, but most of these waveforms in literature people have tried out, and they were not very encouraging. The results were not very encouraging. So I'm not really 100% sure about them, but most of the literature they say that it shouldn't be, means it is not very encouraging from the automotive perspective. Please note that whatever I am talking about is from the automotive perspective, where the ranging and the detection is actually of a paramount importance. But let's say, for example, if you have any other application where sensing accuracy can go down a bit, that does not that is not critical, but you need a good data rate. In those kind of applications, absolutely there are many other waveforms which are doing very well, as we discussed earlier as well, OFDM being one of the favorites in that.
Pallav, little more to add that yesterday there was a lecture by Dr. Amit Mishra where he showed that they could use the LTE and that is GSM signal for that is sensing purpose, mainly like human activity detection. So they have done a lot of research with respect to this signal. So they can refer the yesterday's slide and recording, which had shown that it can be done.
Actually, that's a very good example, sir, you said. So human activity recognition and all of these kind of things, they do not matter so much on the range resolution. You do not have a very high range to be addressed. So,
Yeah, yeah.
so in those kind of cases, that's a very good example where you can actually use that. Even one more example I'll talk about. So there is a company who is actually building based on Wi-Fi signaling within the vehicle, occupancy monitoring and occupancy detection. That's again a very good example, because there you do not require a very good range and a very high resolution, and it's like a compact area within 5 meters. And so in that case, that becomes absolutely like you are reusing the Wi-Fi hardware to actually have a radar functionality within the car. So that is also a very good example.
Okay.
But when we talk about, like, when I was referring to the out of the cabin, where by default our radar needs to perform like at least 100 meters of range with a range resolution of less than zero point 0.5 meters, and at a relative velocity of 140 kmph or higher. So within that constraint, it becomes really very difficult.
So participants, any other participant have a questions? As the Dr. Pallav is a very technical person and practical person, he builds the systems, and he is in the industry since almost 10 years in the different automotive as well as what we call GPU industry.
So I think there is a question for you.
Yeah, that we'll be sharing it, because that is a huge recording that we are optimizing, and we'll be able to send it. Slides I will be sending it by today night. I think no more questions, I believe. So the question is
IRS implementation. Yeah. So means I have not. It's more of a hobby project for me on the IRS implementation. The thing that I am currently working on is on the controller side, how we can actually have the controller which can actually excite the individual patch elements. But I am not an expert in that, to be very honest. So I won't be able to answer many of your questions probably. But if we develop something, we will definitely put it out, and maybe that might be something of interest to you. But soon we are going to have our own IRS module as well, that you can actually purchase for your experiments. So when you buy a hack RF, you actually get bunch of different types of antenna. But what you don't get is directional antennas are not that great. So, and when we develop these kind of applications at that point of time, uh, a good antenna is always a good directional antenna is something which is very good to start with, and that's where I always recommend to invest a little bit on at least some kind of a horn antenna. You can even build it at home if you go to YouTube, and if you just type out building antennas. Like, we build antennas just by cutting out copper plates and then putting copper wires on top of them and then etching them off. It's as easy as doing like that. You should be able to build multiple of these patch, and I'm sure most of you would have some kind of a tool like CST Studio or something like that, where you can simulate some patterns and build those patterns, just print out, cut it, take, like in Amazon you can get copper plates for dirt cheap. Take those, punch in bunch of SMA connectors on one end, hook them up, solder them, and hook them up with copper strips. You are good to go. You can actually replicate some very good antenna patterns without investing much. Can we integrate this with federated learning? See, the concept of federated learning is so the concept of federated learning is basically where you have multiple different systems are actually sending the data to one or multiple cloud systems, where the anonymity of the data is the key concept. So federated learning, let's say for example, it's widely used in healthcare and so on. I don't see an application where we can implement federated learning as such on radar sensing. But if there is something that comes to your mind, I'll be very interested in discussing that. I think the formulation of 6G is still under yeah. Professor Hiramat would be the right person to tell you about 6G. I come from mostly radar signal processing side, not so much a communication expert, to be very honest. Sir, if there is any specifics on the speed and the latency requirements of 6G, I'm not aware of that.
Refer to the 3GPP release 20. So their recent specifications are given.
Okay.
And there is a one saying that, let me know when new model will be available again for wonderful session and contact. Would you like to be in contact? Please share your LinkedIn profile. Somebody has asked, Madam Neha Rani. So you can.
I will share my profile. Yeah, so the IRS information about the IRS module currently that we are building, we expect it to expect to launch it by January end, and we will update it on LinkedIn, so you can follow over there.
So I think there are no more questions. I think we can end the session. I thank Dr. Pallav for a very interesting and practical lecture about the joint radar communication sensing, and very insightful, and many people had asked the practical questions, and you could answer them. Thank you very much.
Thank you, sir, for having me. Really appreciate it. And
Okay.
I hope I could impart some information from our work.
Thank you, Pallav. Very nice. Thank you. So all the
Thank you, sir.
participants, thank you for joining. So again, tomorrow we'll be starting from same timing.
Thank you, everyone. Have a good night.
Okay, thank you. Good night.
Thank you, sir. So I am ending the event.
Yes, sir.
Okay.